All right, I hope you enjoyed that video showing that really nice explosion when that sodium metal hit the water. And now you can fully understand the chemistry of what was going on. The water itself was being reduced by gaining 2 electrons. My favorite part is how they were shielding themselves with the splashes of strongly basic water with their umbrellas and not wearing eye protection. Not advised to do that. It is a very dangerous situation. The chemistry is clear. That stuff coming out of there is quite nasty. But that's the overall reaction right there. And these half reactions tell the story. And I really personally believe this is a great way to attack these problems other than just memorizing this whole equation. Try to understand the actual redox chemistry that's going on there. Okay, this next type of reaction is called a disproportionation reaction. And it's just a fancy way of saying you can have a reaction where one element is both oxidized and reduced in the same reaction. So it undergoes both processes. So in order to do that, it must have at least 3 oxidation states, and an intermediate state kind of comes to play in there. For instance, copper can be copper 2, it can be copper 1, or it can be plain copper, which has an oxidation state of, fill it in, 0. Right. Okay, so there's your 3 possible oxidation states. Now, that's all that's going to be given to you, like on the AP test. And they'll say, what's the chemical reaction going on when copper 1 chloride sits on a shelf and all of a sudden you get some impurities in there? What happens? Well, the copper ion right here can gain an electron to form solid copper, and then the copper plus 1 ion can also turn into copper plus 2 by losing an electron. So it can kind of go both ways. So that copper sitting in the beaker, when it's sitting there on the shelf for a long period of time, can do 2 things. That solid copper can eventually come out of there. This is not a fast process. It'll take a long time. That's what they mean by extended period of time, a year or 2. And all of a sudden, that copper 1 chloride is acting like it has some copper 2 ions in it. And what's that crap on the bottom? Why, it's elemental copper. So you end up with this pure reagent solution that has 3 different forms of copper in it, and that's called disproportionation. And again, those electrons on either side will cancel out, and you get the 2 positive copper ions. One turns into solid copper, and one turns into Cu plus 2. And it's not just like a metal ion turning into 2 different forms. So you'll see some other examples, like oxygen can do it, because oxygen can be -1 if it's a peroxide. It can be -2 in its normal state, or as its elemental state, it would have an oxidation state of 0. So 3 possibilities. So you'll see this happen. Now this is part 2. Like elements existing together in 2 oxidation states can undergo redox reactions to produce a species in an intermediate state. Kind of a tough one to define just yet, but if you were talking about solid iron filings are added to a solution of 0.5 molar iron 3 chloride. Well, the iron 3 chloride is soluble, so you're going to have a Fe plus 3 ion. Is going to possibly gain 1 electron because, you know, iron, the most common oxidation states using your yellow sheet, and now kind of committing that to memory, is plus 2 and plus 3. So here it is gaining an electron. The oxidation number goes plus 3 to plus 2. That's reduction GR. All right. Now, the solid iron will do this. It will act to actually give off 2 of these electrons. It's because of this, the type of iron that we want in our diet. Sometimes, this might be something else we can try in class. If you take an iron-fortified cereal, it's obviously the ionic form of the iron that we want, but they'll add elemental, pure iron, like metal iron, in the cereal to help stabilize it with this reaction here. And if you grind it up in a blender real fine, you can take a strong magnet, and out comes little shavings of metallic iron in the iron-fortified cereal. It's obviously they were trying to lock those ions in that we can utilize in our diet. But solid iron can react with the Fe plus 3 to make 3Fe plus 2. So that would be one of the reasons why to add that solid iron to it, so you could end up with this more fortifiable iron for the body here. So that's kind of an interesting little chemical reaction there. Okay, so so there's the 3 different forms of iron that happen, and that's just kind of another example of you can add the 2 forms together to essentially favor forming that 3rd form. So that's kind of the second variation of this, as opposed to the ion sitting on the shelf and breaking into the 2 different forms. This one, you add the solid to the one of the ionic form, and it's usually the one that has the higher oxidation number that you add the solid to. So combustion reactions, very obviously good example of oxidation reaction. You can see, since oxygen is always going to be going from that form, from 0 to -2 in the products, carbon dioxide and water, and in complete combustion, those are the products. You can get carbon monoxide and carbon, but this is complete combustion. When there's plenty of oxygen present, you want your furnace to burn that way and not make carbon or carbon monoxide, certainly. And get a carbon monoxide detector if you don't have one. These are the months you really need them. So anyway, it's just a nice little balanced chemical reaction. As you can see, it's a redox reaction. The oxygen is going down, that's being reduced, and whatever the hydrocarbon is, that one is usually oxidized by reacting with oxygen. That's where the name kind of originally came from. Now, there are special examples of combustion reactions. So if you're not burning a hydrocarbon, for instance, sulfur will combine directly with oxygen to form sulfur dioxide. Just learn it. Calcium will form calcium oxide, which is a solid. Both of these are solids, so they'll burn to form a solid. So these are more kind of, combination reactions. But again, another type of redox reaction where the oxygen is going from 0 down to -2, being reduced. The sulfur from 0 up to +4 there, being oxidized. Okay, so those you just learn them, know them, live them, that kind of thing. All right, so acids, they will donate protons. So we dabbled a little bit in acids yesterday. So now is a chance to throw in some of the types of reactions. Okay? This is a strong acid, one way arrow, that's a strong acid, one way arrow, and you can see it's dissociating into its constituent ions there, these aqueous ions, and near 100% ionization. All right? So when we look at doing a redox reaction in an acidic solution, all right? I'm sorry, I gotta pause here for a second. Okay, sorry about that little interruption here. So, if you were talking about all strong acids except nitric acid, it's going to behave a little bit differently. Metals will react quite nicely to form a hydrogen gas. You drop a piece of metal. You might remember the little demo we did. Put some magnesium, little bubbles, and then you light them, and then it kind of goes boop. So that is a nice little reaction that occurs here. This is going to be like +1 or +2 because it's a metal, maybe +3 aluminum. But if you have a situation where A equals 1, you would have to multiply this all through. But in this case, they said let's take one that has a +2 charge, so that all balances out nicely, and you have the 2 electrons that were gained over here. This would be 2 because of the +2 charge there. So then those electrons will cancel out nicely. So hydrogen pulls electrons out of the metal, all right, to form hydrogen gas. You can think of it as being that way. And that's what's going on right here. Okay, so this is a oxidation or a loss of electrons. So the metal is getting the electrons pulled away from it. So when we look at an example, so you're writing a balanced net ionic equation for magnesium placed in a solution of hydrochloric acid. So there's magnesium. Obviously, the solid then can get its electrons pulled away from it. There's your Leo. There's your hydrogens. Put the 2 electrons for the 2 hydrogens, giving you H2. And that's how magnesium will react with 2 H pluses to form magnesium ions and hydrogen gas. So that's why when metals are placed in acid, they tend to bubble up hydrogen gas. Again, another great example of oxidation reduction. And tomorrow, we talk about a really neat application of redox in balancing chemical equations. So, got another assignment for you to work on. Yay! All right, bye.